Okay, welcome everyone to this continuation of what is quantum topology. We are already at part 5. And last time I explained or I introduced, or well, I recalled, whatever you want to call it, the cobordism category or the tangle category, which is one of the main players of quantum topology. And today I would like to tell you a little bit about other main players of quantum topology, because quantum topology really is this idea of sending topology into algebra, right? So there should be some algebraic categories as well. And yeah, so let's have a look at a few examples of categories with a focus on algebraic categories, right? That's the whole point. So I think the examples of a category, two of them, they're essentially the same, but we like that one more in quantum topology. But anyway, the two examples of a category is a category of sets, where the objects are sets and the morphisms are maps. No? And this is like really the prototypical example that you can always have in mind. A little bit nicer, because quantum topology really is a version of linear algebra, is the category of linear algebra. Some people call it vector spaces. It's really the category where you can play with linear algebra games. And particularly if I put an FD in front, which really just means finite dimensional, then it's really linear algebra, right? Finite dimensional matrices and all that fun stuff. In general, a bit more general. There could be fancy infinite dimensional vector spaces, which we most likely not use at all. But anyway, the category of vector spaces over some field. Right? So objects are vector spaces, k squared, something like that, and morphisms are k-linear maps. And look, this picture here says that somehow the left side, the green one, so this one here, is somehow an enrichment of the other. Because if you just forget that you have vector space is an underlying set, then you get to the set picture. And it's really just a linearization of the other side. And yeah, in quantum topology, we definitely like linear algebra. So I usually will only talk about vector spaces. Everything is vector spaces. Because one of them is the linearization of the other. There's always also a version in set if you want. But I really do like vector spaces. So this is kind of the examples, or the example, or whatever you want to call it, of a category, right? The other example of a category, which we won't use so much, but is more traditional category theory, is the category of categories. Because category theory somehow always wants to refer to itself. Category theory is this idea of putting the focus on relations, putting the focus on not on objects, on relations, on morphisms. Yeah, and in particular, if you put the focus on relations, you should whatever you have collected, whatever you have created, you should collect it again in a new category, and then again look about relations between the new objects. Yeah, in the category of categories, now the objects are categories, and the relations, the morphisms, the arrows are functors between them. Yeah, so the object could be something like the category of rings, the category of sets, the category of abelian groups, mod z, so z modules abelian groups, that's the same, category of groups or something like that, and you have various relations, functors between them. Right? So the slogan always of category theories is everything is a category, and we really should focus on relations between the objects we like. Right? So the most important thing about categories are actually the relations between them, which will be the functors. Here, just some very easy functors. So you can forget the ring structure and you can just look at the underlying set and you end up in set, right? So you can forget the multiplication, you can just look at the underlying addition and you end up in abelian groups, something like that, right? But anyway, category theory is always a slogan of putting everything together in one collection and study relations between them. So in that sense, this is also the example of a category, right? For quantum topology, this one is the more traditional one, but for category theory itself, categories are the main crucial example. So the category of categories, not categories. The category of categories is the main crucial example. And of course, you can keep on going. You can talk about the category of functors, and then you have a new layer of informations between them or something like that. But more important for quantum topology is, so here's a character table. The character table of the symmetric group. So hopefully this is magma code. Hopefully it's kind of self-explanatory. G is the symmetric group, access the character table, and this is how it looks like. So it's this little beast down here. So there are 3 simple characters, and there are 3 conjugacy clauses, and this is a character table: trivial representation, sign representation, and a 2-dimensional representation. And these are group representations. So somehow quantum topology is built upon generalizing the example of group representations. This is not quite the category of group representations. This is like its combinatorial shadow, if you want. But anyway, I don't have a really good picture of the category of group representations. I think I like this picture for the category of group representation. That's the linear shadow, and you somehow want to mimic what you see in group representations, right? The character ring. So this whole thing is usually called the character ring because you can add and multiply characters. And quantum topology essentially, I think, can be divided into 2 bit different pieces. The topological part, which is some version of tangles, and the algebraic part, which is some version of this, actually. Usually I talk about vector space itself because it's a bit easier, but we really need a bit more structure, and we really want to think about some generalization of group representations. That's what quantum topology is all about. And the usual category theory slogan says they form a category. And of course they do, the category of group representations. Yeah, just a reminder, the category, well, objects, we don't care about objects. Morphisms, sometimes arrows, they are really important, the relations between things. And then the usual axioms, they essentially only have 2, associativity and identity of identities. So whatever type of relation you have between categories should preserve those little 2 structures here, right? Like a set with arrows, if you want. That's why I always draw these type of pictures, right? Like a set with arrows inside. Like a group with multiple start points. Why is that? Well, group is like a multiplication, right? You can compose arrows, but now you have multiple start points, right? That's somehow that thing. Or like a universe where relations matter. So that's really what a category is supposed to be. Relations matter, right? So group morphisms are more important than groups. Set maps are more important than sets. And for all of them, I say that again, maybe in this example, the name is a bit strange because the maps are more important. So it should actually be named after the maps. So it should be called maps, but it's called set. And indeed, there are many, many ways to build a category upon sets. You could look at relations or something like that, binary relations between sets or something like that. And you get a different type of structure. But traditionally, for some reason, people always call them or name categories after the objects, or at least most of the time. Our little tangle category is actually an example where the name is actually correct, because it's named after the tangles, where the objects are just stupid boundary points, right? Imagine it would be called boundary points or something like that. Who would know what that is? Anyway, yeah. So kind of what does quantum topology study? Well, we always have categorifications of certain notions, and you need some form of structure to get started, right? Categorification of set is a category. Categorification of a monoid, that's kind of the next step, is what we will see. It's a monoidal category. Categorification of an involutive or commutative monoid is a pivotal braided category. It's kind of the topological data that we will see. But we also need something like rings or algebras, and these correspond to those types of categories. Yeah? So one ton has more structure than a plain category, so in order to do something, we actually need more structure. And that's what you usually need to do. Just think about the theory of all groups. There's not much you can do. There are too many groups, there are too many counterexamples. The theory of all groups doesn't have very exciting theorems, so you enrich the story a little bit, and it gets somehow much more exciting. And the whole point is kind of trying to find the right balance between being too specific and being too general. And it's kind of these type of categories, in hindsight, but nowadays it's kind of well known, kind of manage to have a really good balance between those two extremes. Anyway, I hope you enjoyed this video, and I also hope to see you next time.